Okay, so we have spent a lot of time and we've looked over different types of bonding, and we've looked and we said, okay, this is ionic, this is covalent, this is polar, this is nonpolar, this is, all the different things that we've talked about. So now let's take this understanding, expand on it, and look at how that's going to relate to when different molecules get together. So not things that are bonding together, but what's happening between two molecules. Okay, so to do this, we have to be able to look at the molecule as a whole, and this ends up being fairly easy, especially with what we've already learned. But let's look at molecular polarity really quickly. I don't think that this will take much time because there's a really quick and easy way to determine this, and that is just going to be using this acronym. Okay, SNAP. Basically what that means is if it is symmetrical, that's a long word, and I don't even know if I spelled it right. It is nonpolar as a molecule. It doesn't mean that the bonds in it aren't polar as a molecule. If it is asymmetrical, it is going to be polar. Okay, so let's look at a couple of examples of this. Easiest example, H bound to H. Okay, symmetry lines, we've got one there, we've got one there. This side looks like this side looks like this side. This is a symmetrical, so this is nonpolar, which is very easy because this is also a nonpolar bond, right? Okay, so something a little bit more complicated then. Okay, carbon dioxide. Well, this is a polar bond, right? Carbon to oxygen. Oxygen is very much more electronegative than carbon, so that is a polar bond. But if we look at the symmetry, okay, this looks like this looks like this, so this is a non-polar molecule. Okay, and basically the reason why, get into that for a second, this guy's pulling electrons this way. This oxygen is pulling electrons from the carbon this direction. This oxygen is pulling, so this oxygen is pulling electrons from the carbon. Well, look at these two arrows. This arrow and this arrow are the exact same in opposite directions, so they end up canceling each other out overall. Okay, so yes, this is a polar bond. Yes, that's a polar bond, but they cancel each other out, so it is a non-polar molecule. All right. On the other hand, if I have something like, all right, so this is definitely a polar molecule. It is not symmetric. Okay, so there, this is not the same. So this is a polar molecule, as a polar bond and a polar molecule. Okay. Turns out when I have polar molecules like this, H bound to F, which we just looked at, well, the electrons for this are all right here with fluorine. Let me rewrite that F in here. Okay, they're all over there. Well, we know that electrons have a negative charge, so what we see here is that this fluorine becomes negatively charged, and it's not a full negative, it's a partial negative charge. Yeah. Which we draw in there with this squiggly little line that we call a delta. Okay, and that means that it's partially. It's not a whole negative charge. It's a partial negative charge. And it gets that because the electrons are closer to it. It is stronger than the hydrogen. So the hydrogen then becomes partially positive. Okay, because it's lost the electrons. The electrons aren't next to it. They're over there by the fluorine. Okay? So when we have a whole bunch of these guys in a beaker or in a flask or, just floating around in the air, hopefully not, hydrofluoric acid probably wouldn't be the best thing to have in the air around you. But this partial positive on the hydrogen attracts to the partial negative of the fluorine, and they end up making not a bond but an attraction, a very, very strong attraction between them and forming pseudo bonds, almost bonds between them. Okay, so these guys end up bonding, not bonding, but almost bonding together. Okay, whereas in something like carbon dioxide or HH, there isn't that. There isn't a positive or a negative. So they just kind of randomly bump up against each other every now and again. You know, this guy's traveling this way, this guy happens to travel this way. They hit each other, and then they both bounce off from each other, right? And we have names for these different types of interactions. When I have a molecule like this, I can say that this has a dipole to it. And all that means, like the Earth has a dipole, right? I have the North Pole, I have the South Pole. It is dipolar. Okay, I have a partial positive, I have a partial negative. It is also dipolar. That's why we have a polar bond there. When those two are interacting, so I have HF, and then they have a very strong interaction to another HF, we call this a dipole-dipole interaction. Okay, when they are not reacting, when they are just basically bumping into each other randomly every now and again, we call this a London dispersion force. Okay, London dispersion. All right. If the molecule has in it an OH bond, an FH bond, so what we looked at, or an NH bond, these are dipole-dipole interactions, but they are super strong. So these are like the Superman of dipole-dipole interactions. So we actually give them another name, hydrogen bonding. Okay, and despite the fact that we call it hydrogen bonding, it is not a bond, it is a super attraction. Okay, between the two molecules. This ends up being extremely important in DNA. In life in general has this. This is why water floats when it turns to ice. It just has a lot of different impacts. It's so huge that just about any time it is an answer on a it's on a multiple choice test. Pick it. Okay, there's a million reasons why it can be justified as the answer for anything. So it's a huge concept, but that's all it is that they are, that polarity difference in an here between these two, where the oxygen is negative, the hydrogen is positive, is so strong that you're going to get this interaction between these two things, and that's going to do a whole bunch of different things to it. And we're at 9 minutes, so I'm going to go. Hopefully that helps.